right, everybody, I think it's just about 10 o'clock. I'm gonna go ahead and get started. It's great to see all of you. I hope that you had a good weekend and a productive one and hopefully a little bit relaxing. I had a great weekend. I did nothing all weekend long, and sometimes that's just what the doctor ordered. So I took a bit of a break and relaxed. I got some work done, obviously. I got ready for class, but I didn't have to go driving off to some mountain this weekend, which was kind of nice. Anyway, hope that you guys are doing well. We do have a busy week. This week is a big one for us. We have an exam coming up. So I just want to remind you about a couple of things on the agenda, and then we'll get into this review of determinants again today. So first of all, just to get it all straight, there is a homework assignment due tonight. So it's homework number 8 that is due tonight. You might notice on Canvas that that's the last homework that's posted. I posted the first 8 homeworks right from day 1 of the semester because they are the ones that are pertaining to this first part of the semester. However, on Thursday, like 5 minutes after you're done with the exam, the next 7 homeworks are going to all just drop in and show up, which are the homeworks for the second section of the class. Okay, so anyway, this is the last one that's due this week. This is the only assignment for this week as far as homework goes. It's due at midnight. If you've got questions on it and you're still stumbling through it later on in the day, that's fine. Just stop by my office hours. I have office hours after 5:30 today. So I should be around most of the evening except for a dinner break around 7 o'clock. So feel free to do that. Also, I emailed out to you guys over the weekend. You should make sure that you have seen this extra credit quiz. This one is also due tonight. So these are kind of both due tonight, but in 2 separate assignments. So make sure you submit them separately into the correct locations in Canvas. But this will get you 3 points, free points for your midterm on Thursday for turning that in. I will be grading those though, so you have to get the problems right, obviously, to get the points. And I will try to grade them by tomorrow sometime. I'll be doing this. I'll be doing the extra credit myself, so I won't ask my grader to do those. Keep asking me, by the way, if you're having any questions about where you've lost points on homework. I'm always happy to clarify that if it's not totally clear. I can certainly do that. But anyway, so 2 things due tonight. The extra credit quiz is of course optional, but I definitely recommend doing it. It's kind of a good way to study for the exam, actually. So it could be a good thing to look at. I will post solutions to both of these things either after midnight tonight, or if I actually go to bed early for a change, won't be till tomorrow morning first thing, but I'll have those up for you so that you can check them. Our midterm, as you should know by now, is on Thursday. So this is on Thursday in class. You'll have the entire period to take the test. You don't have to stay the whole 2 hours, but I always encourage people to check their work. If you think you're done early, use that time to just review your EROs or your determinants or your cofactors, whatever it is you've been working on, and try to do the best you can with this. I think you all know what it's going to cover. I went over the resources folder last week. Hopefully you've already been looking at that. Has anybody tried a sample test yet? A little bit, so you kind of have some idea. Hopefully you have some idea what's going on. I have had some office hours the last couple of days. I've had nobody coming by. I'm assuming that means that you're all just doing great with my resources folder. It used to be I didn't have those resource folders and I had a lot more office hour traffic. Now I think it's kind of reversed because I have all those resources. People are looking at that. At least I hope that's what's happening. By now, everybody should have hopefully had a chance to look a little bit into that folder. Remember, you don't have to do the whole folder. Just whatever you have time for, whatever you think would help you the most. There's 3 chapters, right, that you need to study for this exam. And you probably have an idea for yourself where your strong points are, where your weak points are. And you can use that folder to hone in on maybe some of those weaker points to shore those things up a little bit for Thursday. Okay, so any questions about the stuff leading up to our midterm here for Thursday? Also, in addition to today's office hours, I don't normally have office hours on Wednesday, but I am going to do it tomorrow. Just because of the exam. So if you have things you'd like to talk about tomorrow, I'm going to be in the morning. What a miracle. About 9 o'clock tomorrow morning, I'll stay until noon, and then I'm gonna go do some stuff in the afternoon for a while, but I'll be back in the evening again. Starting at 8:30, and I'll stay as long as there's people around with any kind of questions. You can come in person, you can come in Zoom with any questions you have. So these are extra hours that I don't normally do every week, but I'm gonna do them just in case anybody has last minute questions. You can come in to my office hours and just say, oh, I don't really understand how to do the Bernoulli equations. Could we just work one out? And I'd be glad to do that. Or I don't remember how cofactor expansion works. Could we practice that? If you would benefit from something like that, feel free to stop by. I'll definitely be around. I want everybody to do well. And so as much as I can help, I'm willing to do that. Okay. Great. I think that's all I have for announcements. Anybody have any questions about any of that? Also, let me mention that after the exam on Thursday, there will not be any immediate homework due. Your next homework assignment, which is homework number 9, won't be due until next week on Friday. So it'll be a pretty good stretch of a break. But over this coming weekend, I am going to give you another extra credit. It's kind of weird. I call it extra credit, but then I say it's required. There is a video that I'm going to ask you to watch. I think I said this in my email, but I just want to remind you that this is coming. It's a pretty long video. Most students will want to maybe chop it up into 20 minutes here, 20 minutes there, because I think the whole thing is about 78 minutes long. And it's to give us a boost into chapter 4. Chapter 4 is the longest chapter in the book. It's also more abstract, so it's going to take us a while. So I want to get a good boost into it by having you watch a video over the weekend. So that will be coming. All you have to do to get the 3 points of extra credit towards this midterm that goes with that video is just watch the video and take notes on it, and then just submit them by the deadline. As long as you do that, you'll get those points. So that's that. All right. I think I've gone over everything. Any questions? So far, so good. Okay, great. Yeah, so this is a pretty big recap. If you didn't want to write it all down, I suppose you could just take a picture of it. It's kind of summarizing a lot of the material about determinants. Let me get my camera on it here. So I've got 2 columns, right? On the left side, I wanted to remind you about some properties of determinants, right? We had 7 of them that we kind of went over last week. The first 3 have to do with the effects of EROs on determinants. The idea there was that we could use a strategy where we use elementary row operations to bring more zeros into our matrix. That can only help make our determinant easier to calculate, right? So that is a strategy we could use, is to use these EROs. But if we're going to do that, we have to know how the EROs affect the determinant as we go along, right? So for example, if I permute 2 rows of a matrix, the determinant is going to flip signs. Okay, or if I multiply a row through by a constant, the determinant is going to get multiplied by that same constant. Turns out if I add a multiple of one row to another, nothing changes. That's kind of convenient. There's no effect in that particular case. So it's good to know these things here, of course. And then some additional properties while we were on the topic of this. Transposing a matrix does nothing to the determinant. If I do scalar multiply a matrix by a constant, we have to be a little careful because that scalar gets powered up by however many rows the matrix has, because each row is picking up a factor of k. So if I multiply the entire matrix through by k, I'm going to power up the determinant by k to the nth power, right? Question?
If there's an inverse on the outside of the, like k to the a and then inverse, would the k to the n still be inverse?
So if you had, so I think what you're saying is if we had this.
Yeah.
Right, so what you would do here is, so that goes to the 7th property. The determinant of an inverse of a matrix is the reciprocal of the determinant of the matrix inside. So the determinant of this would be 1 over k to the n times the determinant of A. So you're kind of combining some of the properties together, which is good. We're gonna practice that. in a
Yeah,
second.
that's what I was on.
Yeah, but be careful, if it was the determinant of k times A inverse like this.
Yeah.
Now the A inverse is being scalar multiplied by k. It's not taking the inverse of k times A. These are two different things.
Yeah.
Depending on how you put the parentheses,
So,
right? Just from an algebra perspective, the quantity Ka inverse is not the same thing as taking A inverse and then just scalar multiplying it by k. So you'll get different answers. Clear enough?
yeah, thank you.
Great, great. Also, determinants respect multiplication. They work real nice with that, but they do not play nice with addition. So there's no formula here for the determinant of A plus B in this case, right? Okay, so this is just a nice little review of the properties of determinants over here on the left side. We went through all of these last week, and some of these are being touched on the homework that you're working on for today. Yeah. So far, so good? All right. In the right-hand column, I made a totally different a list of points. And this is what is the importance of the determinant. We also went over most of this last week, and I just wanted to rehash it with you one more time here. First and foremost, this whole chapter kind of started off with being a test for invertibility, right? So a matrix is invertible exactly if and only if the determinant is not 0, right? So that's a good thing that we should know. We can test for invertibility here. As long as the determinant is not 0 and my matrix is therefore invertible, we actually can find the inverse totally using a determinant-based approach. And that's called the adjoint method for A inverse. And I've got the formula in the box here. By the way, everything in these boxes you for sure want to know for Thursday, right? So you've got A inverse this time. It's 1 over the determinant of A times the adjoint of A. So the adjoint of A, I went through this last week. It's just the transpose of the matrix of cofactors. Okay, so there's a little bit to remember here with the formulas, but all of this is just plug and chug, right? Cofactors are literally just plugging and chugging, calculating determinants. So as long as you can do the plugging and chugging and you know the formulas, you're going to be in pretty good shape. Okay, so that's that. Then we had this idea of actually solving a system of equations by using determinants. And this was the so-called Cramer's rule. Again, this will only work if A is an invertible matrix. You can see the determinant of A in the denominator. Anytime I see the determinant of A in the denominator of an expression, I know that it will only make sense if A is invertible, right? Invertible is the only way that that denominator is not 0. But anyway, I reminded you here of the formulas. I'll let you review from last week. We had this B sub I where we substituted the ith column of A with whatever the right-hand side vector was. But we did an example of this and kind of just hopefully got somewhat familiar with Cramer's rule. Okay. And I did not talk about the fourth point yet. I put it back on the board here just because my list is, it's a nice place to put it in my list, but I didn't really talk about the geometry of determinants yet. I am planning to do that very soon. So anyhow, any questions about either the properties or the importance of determinants? Yeah, Jose?
For Cramer's rule, you can substitute into any column of the matrix, right? Or
It depends which unknown you're looking for. So if you're solving for the ith unknown, then you need to replace the B vector into the ith column of the matrix A in the numerator here. So it's not just arbitrary. If I want to find all of the unknowns, then I have to actually find all of these B1, B2, B3, B4, and so on, and do it repetitively to get each of my unknowns one by one. Yeah, absolutely. Clear enough? Everybody okay out there? Up with determinants, right? We really wanna celebrate them, we're gonna use them. We have at least 4 great reasons why we should care about determinants here. This board, gosh, it summarizes a lot of chapter 3, doesn't it? I don't have the cofactor expansion theorem up here today, like the actual nuts and bolts of calculating determinants. But the properties are all here and the reasons that we care are all here. That's like a lot of a summary right in one little table. So this is worth printing it out and put it under your pillow for the next couple of nights. Get that information into your head for our exam this week. Okay, let's practice a little bit. I've got a warm-up problem here on the board that might be a good chance to see how we're doing with these properties and kind of put a bunch of them together. Let's suppose I have 3 matrices, A, B, and C, and they're all 3 by 3 size. And the determinant of A is 2, the determinant of B is 3, and the determinant of C is 5. And then the question is just asking us, I kind of made this up just for fun. Let's find the determinant of 3C inverse times the inverse of B transpose A squared times 5A. Okay, so let's just see how we can do with that, all right? And this is mainly going to be focusing on the properties on the left side here. I see transposes, I see inverses, I see products, right? I see scalar multiples. So I'm guessing we're going to use several of these properties, particularly 4, 5, 6, and 7 in my list to help us to do this. Okay, so let me just, for notational simplicity, I'm going to call the entire matrix capital X. So I don't have to write it down again. The determinant of X, if I want to think of it as the entire thing. Can somebody help me with how I might start breaking that down? Adrian? Yeah, each of these into its own determinant. I have 3 parts here, right? So property 6, let's just use property 6 here. I'll put a little label of which property I'm using as I go along. Let's break this into the determinant of 3C inverse times the determinant of B transpose A squared inverse times the determinant of 5A. And that will allow us to work on each of them one by one. So that's by property 6 that says determinants respect multiplication. Okay, now let's take a look at this first one. Let's just do them one at a time. I have C inverse. But then I have a scalar multiple in front. And so the scalar multiple property is property 5. And what it says is if I take the determinant of a scalar multiple of a matrix, I have to power that multiple up to whatever n is. Now, n is always referring to the size of the matrix here, right? So in this case, n is 3. So this 3 is going to get powered up to being a 3 cubed, right? And then the determinant of C inverse would be what, by the way? The reciprocal of the determinant of C, right? By property 7. So this would be 1 over 5. Okay, so here I'm using property 5. Here I'm using property 7, right? So I'm trying to practice all of these properties right here. Okay, so I've got 3 cubed times 1/5. And then the second term. Now here I'm taking an inverse. So actually, before I even take a breath, I'm just gonna get my reciprocal going because the property 7 says that if I'm taking the inverse of anything, the determinant just gets flipped to the denominator. So by property 7, this is gonna be 1 over the determinant of B transpose times A squared. Now B transpose, what's that determinant going to be equal to? Just 3, right? It's the same as, so transpose has no effect. Transpose has no effect. So I'm just going to put a 3 there. And then I have the A squared. What would be the determinant of A squared? The determinant of A is given to us as 2. So A squared by the multiplication property, number 6, A squared would have a determinant of 2 squared. And I actually sometimes prefer to just write it like that, 2 squared. So this one is using, I guess we're using almost all of them now. We're using property 4, 6, and 7 to do that middle term. Okay, and then finally, last but not least, the determinant of 5A. Well, that fits nicely with property 5. I'm just gonna get 5 cubed times the determinant of A. So 5 cubed times the determinant of A, which is 2. So there you would have it. And guys, if I put this on the test, something like this, which I have been known to do, it's almost better to leave it like this. If you clean it all up and give me a single final answer, that's okay, but I'm still gonna want to see this work. I won't accept, I won't give credit for just a final answer that doesn't show me some of these individual parts to the answer. Max?
You want us to write like all the like steps of
The reasons, it's usually a good idea. Yeah, I mean, I probably would accept it without those reasons, just because I know where you're getting these from is from our list of properties, but I'm giving them to you here mostly just because I want you to be able to look back in your notes and find them later. So I don't know if did anybody clean this up and get an answer? 150? I could believe it. I actually don't know what it is. I didn't work it out. But that seems probably to be right. Yeah, you've got 9 times 25, which is,
27.
I am actually not sure about this. Let's see, 27 divided by, I just want to combine the threes. 27 divided by 3 is 9. And 5 cubed over 5 is 25. So 25 times 9 is 225, and we're cutting that in half, right? Can I fix this?
Yeah.
I think it's supposed to be 225 over 2. Anyway, I really don't care that much. So you can check me on that. I think I have that right. I should have worked that out before, just to be sure. Let me give you another warm-up problem, but this next one is going to be more conceptual. And it's actually off of the review session that's in the midterm review folder. So I have actually put this next one, I have actually put it on an exam before. So this is a typical type of example. If A and B are n by n invertible matrices. So if A and B are n by n invertible matrices with AB equals negative BA, prove, so this is theoretical, prove that n is even. So guys, this exam is not going to have a ton of theoretical parts to it, but it could be 15%, it could be 20%, something like that. I might also, with theoretical items, I sometimes will give people a choice, choose one of these 2 things to prove or something, so you have a little bit of flexibility. But this one, the very first time I put it on an exam in my class, almost nobody got it right. And so then what I had to do the next time I taught the course, I was determined to get people to get this right. So I added a hint that would help make this a little easier. And my hint was use determinants. Now, you probably already expected that since that's what we're talking about this morning, but the hint would be maybe to use determinants. So as you read the problem itself, there's no mention of determinants anywhere, right? So if I'm saying use determinants, what that means is that we are going to need to infuse them into the solution, right? We're going to have to introduce them somewhere. Is there a way to bring determinants into a problem that on the surface of it never mentions determinants? If I'm going to use determinants, it has to be determinants of a matrix. Do we have any matrices here we could take determinants of? What matrices do we have? We have A and we have B. We also have this equation here, right? Would you guys agree that if 2 matrices are equal, then their determinants have to be equal? Can't you just throw a determinant in front of both sides? and still have a true statement. You'll be turning a matrix equality into a numerical equality, right? Because determinants are numbers. So we could certainly do that. By the way, we all know, I hope we all know, we can't switch the order here. The order of matrix multiplication cannot be arbitrarily changed. So I have to leave it in this order. However, if I change this matrix equation into a numerical one, as long as I'm working with numbers, I know I have a lot more that I can do with that, right? The numerical algebra is pretty straightforward. So let's take a look here, guys. We can just go ahead. This is the key idea, actually, is to just go ahead and take the determinant of both sides. So you just take your original matrix equality and you just hit the determinant in front of both sides of that. And now you're looking at the left side and the bells should be going off. Okay, determinant of A times B. I know a property for that. So by property 6 in my little summary, we can write this as determinant of A times determinant of B. And then on the other side of the equation, okay, so now what about the other side? This minus sign is really like a K value. It's like a scalar, right? So you have like a negative in front of a matrix, and that negative gets pulled out to an exponent of n. So this minus sign becomes a -1 to the n times the determinant of BA, which I'm going to break down as determinant of B times determinant of A. Oh, I think I'm starting to see it now. This is nothing but numbers. This is a number, this is a number, this is a number, this is a number, this is a number. I don't care what order things are written in anymore. That doesn't matter when I'm dealing with numbers. What do you suppose I might want to do next? Yeah, go ahead, Trevor.
Also the power so that you have it as an even power to prove how it would all work out.
I have to prove that it's an even power, right? So I don't know that yet.
Oh.
That's where I want to have my punchline at the very end. But just algebraically, guys, just looking at the left side, looking at the right side, what would you want to do if you were back in high school algebra? Yes.
-1 to the net has to equal 1 for that to be true.
Okay, you've got the right idea. In terms of my next step, what I probably would recommend is canceling from the left side and the right side. Now we have to be careful, guys. You cannot just cancel. Okay, so I hope nobody ever has tried to do something like this before. This is a very true statement, but I hope that we're careful about canceling because you can make a big goof if you cancel a 0. Is that a problem here? Could that be a problem here? If so, how are we going to address it if it's a problem?
They're invertible.
Oh, we don't have to prove that they're invertible, do we? We were told that they're invertible. What do we know about an invertible matrix?
Oh, it doesn't mean 0.
The determinant is not 0, right? So because A and B, say they gave us this information, we're allowed to use it. So if A and B are invertible, then their determinants are not 0. As long as you're not canceling a 0, life is good, right? Everything works. So I can do that. So let's just mention, since A and B are invertible, guess I'm gonna come over here to finish this argument. The determinants are not 0. Okay, so the determinant of A is not 0, and the determinant of B is not 0. And that's awesome because that means I can cancel the determinant of A and the determinant of B. So thus, we can cancel to obtain, after I've canceled, on the left side, nothing is left. There's just a 1 there. It's just an empty 1. And on the right side, the only thing left is -1 to the n. And now you're asking yourself, well, what does that tell me about n? And you all know that this would mean that n has to be even, which is exactly what it asks us to prove. Prove that n is even, right? So hence, n is even. Questions about that? Yeah, so don't be surprised if I ask you a slightly theoretical question about determinants. It will almost certainly be using these properties, right? That we've been practicing here on this little recap. That's definitely something that I think would be good for you guys to be familiar with. Okay, I tell you what I'd like to do next. I have a group work that I think would be, this is just more practice with determinants that I think we could do today. Again, I'm not really doing any new material for this exam today. It's just all kind of reviewing what we did last week. On this group work, you're going to recognize that some of these problems were from the homework, and actually one of them I did last Thursday in class. So I crossed it off. Problem 1A, you can skip that. But what I'd like to have you do, especially with your group, is look at problems 2 and 3. I think those would be really good. Tell you what, let's send these papers kind of sideways instead of back. I'll just move this side. This is group work 5. And what I'm gonna do is get everybody a copy of this and then let you guys work on them on the whiteboards. 6. Send those down that way. And here's what I want you to do, guys. Can you please grab 2 or 3 other people and get out of your chairs? You can use the whiteboards anywhere around the room. We're going to erase everything so that you can have plenty of room to work. And I'll come around and give you guys a hand. Let's do it. You can introduce yourself to somebody you haven't met. That's totally cool. But I don't want you just working alone. Let's have some partners. Thanks, Reed.
I don't know why. I know that's called better.
They pay me the big bucks for them, and they're beating me to it, so. If you want some of my paycheck. What's that?
We know YouTube can kick off. You're gonna not have to.
Then I'm gonna like ride off into the sunset.
Yeah. Just focus on 2 and 3, right?
Yeah, 2 and 3. Work on problems 2 and 3, guys.
Oh, okay. Just kidding.
Got more time, to come back to it. We'll start with.
Okay.
Thanks.
Yeah, well.
Okay.
What you guys wanna, you wanna work, and we got to see, yeah. Yeah. I'll do it.
Yeah, and stuff like this, you would not. Yeah, looks good, looks good. I would have.
Bring it down a little bit.
Yeah.
I think I'm-
Yeah.
Nice.
You wanna like.
Keone, something like that, you could just totally leave it like that. Yeah, I don't care about, we're not gonna use calculator on anything, so you just leave it like that and good to go. Yeah, that's it. Yeah, I don't actually even know what that number is. But without a calculator, I'd have to work pretty hard. 3125. But then you have to multiply that by 48. Yeah. No thanks.
Is that?
Yeah, that would be fine. That would be totally fine. I like that. Yeah, good. Good job, good job. Nicely done, guys.
You're doing all my.
Those and the.
Like the ones that are like.
It's 81 times.
I sweared it.
But when you get to.
He said it doesn't. Wait, what?
Now, something like that, you could read it that way. Yeah, I'm not gonna let you use a copy here on the desk.
Yeah.
So it's gonna be okay, because that's 25 times 250. Yeah, it's not an easy, just leave it like that.
Okay.
And you can move on. Oh, it's good so far. It's good. It's doing okay? Nice. I like it, I like it. Awesome.
Yeah, they raised it.
Hey. Yeah, it's good. Like it. Nice, nice, nice. More guys, and yeah, just I've been telling everybody, leaving answers like this. Totally okay. Yeah. Leaving an answer on something by this. Good job, good job. Looks great. Anybody need help? Yes. Outside of everything, right? So that's. So your answer for that is gonna be to just put. Way on the outside.
Oh, yeah, well, we just provide the cable content.
Anybody need help? Do we need like actual?
Oh, yeah.
B, yes. Oh, it's A, B equals A, C. Oh, actually, I don't think we've just. I'm the white. We haven't quite allowed. What I have done with you before is I've said, well, if B is equal to C, and I want to multiply this through by A, I can't do it like this. Because here you're putting it on the left side, here you're putting it on the right side, the order math. So that I know, but I haven't done this. This one is basically, it's just assume the daytime is equal to the pregnancy. And it's true. It'd be as easy as how do you justify it's because A is invertible. Because A is invertible, I have an A inverse that I can. So I can put like a inverse here and here. This becomes I, and this becomes I, and I goes B to B, and I goes to B. So it's basically just exactly. Now, if I had said, here's a. No, but that's what if I said, if A. And I still want to assume that they like. Oh, why?
I
I could put the A in first here, type A. But if I put the A in this one on this left, this side, then I have to put it on the left of this side. And these like A and the first. Not right. So I think this is, and I even have all six. If it is of this. See the difference?
Yeah.
Okay. Good job, right? And so where is this? Yeah. I do it on the left of one side, then I have to do it on the left of the other side. So that's the basically. Yeah. Single property, I would like to see an example.
I think it's
If something is false, then you can write it.
Oh, yeah.
All right, you guys are good?
Trading things insane. Every single time we do it.
I can't believe it. I know it's. It's negative value. That match. Oh my God. You know what?
Trying to
Change this to a 3. I'm just gonna see if that. Now it's a 6. So this determines.
I can't do that.
That's zeros. Maybe it's might just be a little too nice. What if you just almost finished? What if I just did something? Yeah, you just have to kind of start from scratch. You guys doing okay here, guys?
We're thinking about this.
Oh. It's false. If something is false. It's just want to make specific numbers into a matrix A.
Kind of prove that.
And let's not make it so big and messy. Let's just do something.
It'll be fine. I think it's.
I'm gonna guess that unless I'm really unlucky, I can make any example I want. I bet I can make any example I want. Try this.
That's like.
Just see if it works. What's the determinant of A? What's the determinant of B? And then how does the.
It's on this.
Let's just.
Homework.
And this is even from an assignment. So, yeah. It's always weird to refresh your memory on birds. So once you are here. By matrices, it's like.
Yeah.
Throwing one off of the British cube.
Okay,
Okay, that's how you got.
We know that.
That looks good.
Those good.
And this is good too. And you don't need to say five. And see what you get. All right. Yeah. Good job.
Hey,
How are you guys doing?
Russian
Okay, sounds good.
Oh. Oh, then you're adding. Oh. It's in game since this is one.
Yeah.
No.
When something's false. What's the determinant of that?
Seven.
You get it too, right? What's the determinant of this one? Yeah, two, right? It's the inverse of this.
That's
Six.
Actually, I feel like you could just.
Work that out.
Oh, you said problem one does. What?
That would be, give me an example. I want you to write down the matrices. I want you to tell me what are those individual determinants and what is the result. I have used this exactly.
Yeah, there's a transfer. Look where the CFI is. Is it that way? This is.
Or minus. You have an AP and an AC. We understand. So you're left with the B on this side. Does anybody need help? You guys doing okay? I'll be ready. 3C. 3C says if first A squared B, then is it true that the inverse of A is a 10? Well, how do you decide if the matrices are inverse? It's nothing to do with the right, right. So two matrices are inverse of each other. If you can multiply them out. Well, I take 8 and I multiply it by what they're saying, the image should be, do we get the idea? What we are given is just this. Recall that the doesn't actually have to. Try writing it out. All varieties. If you can get it to fizzle down to just 9. Yeah, that's kind of a cool exercise. How are we doing here, guys?
Here's another question about.
3D.
So we lost the.
True, but that doesn't mean it means.
Yeah. Now we have to use.
Right. Actually, it's true, but it's just we can't determine this to the. So if you actually parts actually don't have no.
Yeah, look,
Yeah.
so.
We have that, we can see lots of both sides, and of course.
Oh, that
first
makes
time,
sense.
so do what? I did. Side A versus side A. So.
Yeah,
Nice. So we know that finished together, it's hard to get the P and CRD.
Oh, Trevor did this, wait, Trevor did A sub B is not equal to 10, and then A multiplied.
Yeah, but he
I take those square. You know what I get? I get A squared, A squared, B, A squared.
It's just like one.
I'm not allowed.
Oh,
What I would like to do is put all the A's together and cross all the B's together on the back. I'm not allowed to do that.
Oh, wait, I think I got it. No. I think I got it. Okay, so it's like 1, 2, multiply by.
So the question would be, and then follow it up with 5. Can I figure out why that will fizzle down to? Fine, you do know this, you do know that every time you see two A's followed by a P, it can't spell.
Oh, wait, that's.
Take a look at this and see if you can see two A's followed by a P.
Okay, so. Is that how?
Anything you see.
Pull this again, but when you're doing this. Since it was fully disabled.
But you're definitely good.
I don't think it's. But we have. We also told them to buy eighteen. Now, you also know that.
Yeah.
I mean,
This one.
yeah, we did.
Turn it songs. Here's probably. Think, just. And then. Not in high school.
Checks are one.
But.
No, like that, maybe. That's the one. And then-
I did it yesterday.
Oh,
I have a.
yeah, so-
They usually say.
You actually. It's like, you ready?
Yeah. Now, here's something. If I.
We know that. This weekend was.
It's energy. Same thing. Cancel the day. But.
It's structure. There's no structure.
If I was staying in versus left of the west side, left of the right side. And while I.
I get there 6:30. 6:30.
Started off.
But why?
Very, very interesting.
It's like trading.
Oh, alright.
So it's like ours.
Oh.
Good enough?
Oh, no, like we're getting up the.
Did you get it?
But like.
You grouped them in the center, right? A squared B.
That's it.
Inside out.
Yeah, you're.
That is, you need to show this. You've got it. Does anybody need a hand?
There's still.
How are you guys doing? The very last one? Okay. So if I assume-
So that means. So I thought.
It's the identity. So that I show that A is one. That's right. But there's a problem. But it is.
All in the back.
And it's all of it.
This thing
It's that Facebook.
now.
It's like, oh wow, this.
You know, that we're locked up for that.
I like it.
So like physically moving in a class.
Did I have another A's? I stay class. It's right next to
Oh,
this. And now also I. All that. Yeah. Professor.
Is the identity matrix to any power?
It is, yeah, it absolutely is. Is there a question? Okay, I'm gonna get out my red pen today, so that I don't have to do it on Thursday, right? The idea is, do we ever divide by matrices in this class? Yeah. I don't want to say that.
Wait.
So just leave it like this. This is totally good.
This is
Never divide by matrices. So this is true, but.
Well, I think I two things. Like if we're.
I tell you what, I actually want to show this to the whole class. So let's do this, so Brandon knows what's happening. Because that's happening. I'll leave you in suspense. Hey, guys. I think I'd like to go ahead and take a 10-minute break. I know not everybody's quite done. I'm gonna do that very last problem for everybody together right after the break. So 3C, if you're still working on it, I'll help you with that as soon as we take a 10-minute break. But feel free to sort of take a little pause here if you want, and we'll come back in 10 minutes and continue. 10 A's and 5 B's. And every time I have 2 A's, the way to do it is you basically look at 2 A's next to JRK. Because this is the assumption really A's and the B right after it becomes just I. They get rid of it. And then you have transfer A's and another one. It's from the inside out. These 2 A's now to what happens. And it just boils it down. Eventually, you're left with not totally the right strategy. Right after, I would have to figure out exactly how to process it. Okay. All right. Good job. Good job. You bet. You bet. Seal. Sorry, just one comment over back there. You see where you have that 1/a²? Take that off. We don't want to divide by a matrix. Yeah, that needs to go. Yeah. Let's erase that. If that's on the board when I leave here and my department chair comes in and sees that, he's gonna ask me, what am I teaching those kids? So, yeah. Yeah, get rid of that. Yeah. Okay. Perfect.
You already taken.
Somebody had some homework problems up over there and I don't remember which ones they are.
That's one it's like, then we just get. Oh, really?
One is point.
That was one. Oh, because it's. Yeah, I know. Yes, because it's inverse of another, right?
Yeah, so I wanted to do it, but we can, the big one, I don't know how he was part of like the draft.
But he wanted to wear it. Yeah. I know we have that, but necessarily it's just. It's just like right on the board.
And those are so bad.
Are you allowed to
like use and then underneath some he didn't convert it. I don't know, I'll do it the way that he's 1/a solder, but everything and then expect it to remember. Write it down.
Strategies to. So I don't know, literally, we want to do that too. I have a problem. Right now.
Which group was over here?
I'm
So determinative A equals doesn't mean that, sorry, determinative B equals.
Like, yeah.
So this.
Sorry, I erased part of So the way to do that one. Don't just, all you have to do for that is if you know that A, B, E, just put an A inverse on the left. The action. I just saw that. I started to erase the parts of the paper. Another part.
Oh, really? Or is it like a new? This would change, right? If you did gauge that then inverse, then versus, that's what I'm asking. Does that change? This is the case. Right now, right now, me, right.
Yeah. And then it's like spice mud, where's the spot?
Yeah. I think I'm pretty 30 otherwise. You do over the event right now.
Guys figuring it all out over here?
It's tried,
Which
but
one is this? Oh, you're working on the last. Okay, I'm gonna show you how to do it. I'm gonna show you guys how to do it.
but we need like at least so actually to get a what direction?
Uh,
I just started plugging stuff in and I was like.
I can't tell from that work. I would say I need a little more steps filled in, probably. Yeah, I can't say it's wrong, but I can't say it's right. It's kind of one of those, it's one of those things. Yeah, right. Oh, you don't know my grading rule. If I can't figure something out and somebody wrote in 20 seconds or less.
I mean, that's
I do go do my grading sessions. That way.
Yeah, no.
Sitting there all day, and, you know, get some more time to stew over people's favorites.
I don't know, I think it's right.
I took a.
It's not right after the.
Wait, was that our time? Right.
No.
And he was a grad, I think he was a grad. Forgot. That wasn't long. I'm not done marking 35.
It's a year.
Yes.
I'm on the model, that's the end. And then do you have a break before your next class?
I have the 130. I took that one out of the but I did that one. I have the items. 12, so I could have get. I go to the basic. No, you definitely got one. I think I just don't want to just have all of that.
Like you, it's like a.
Actually, like.
Did you say you're gonna have office hours tomorrow morning?
Yeah.
What time again?
I'll get in around 9 and then I'll stay till then.
I don't know.
Okay.
It's on the midterm review app. So you can find that easily enough there. Oops, Marco, are you being blinded now?
It was fun and then the transfer.
Transpose does nothing.
No, I know that.
Oh.
The rest of it, so.
This would multiply by 2.
I would literally.
Creating the food. Adding operation does nothing.
How to AutoCAD.
About it. That's it.
We don't set it right.
It's like every midterm, it's on the same day too.
Like, I never been in that class.
I think I did, because the grading was so heavily like. didn't go fast enough. It is too loose. The one thing was 2 games. Yeah. Well, they'll probably be there. They'll probably be there. Let's just go to as much of the office hours as we can. They'll probably end up being. Did you make a group chat? I think that would. It's just to like not. Just to keep.
Yeah. That is. Oh, no.
Hey. Didn't New York Times take away the daily? Bro, they actually locked the mini. That's crazy. They locked the mini. You have to subscribe to play the mini crossword. Yeah. What about the word? Everything else is the same. That's the good word. Okay, so you can get it in fewer guesses. Okay. All gray. Oh my gosh. Yeah.
Bro, I struck out on like I think 2 or 3 in a row one time. I almost gave it.
Right, persevere.
What's your pocket streak?
Non-existent. I used to play every
You know,
day.
my problem is,
Senior year.
I go hiking, and
Oh,
then I have no internet for more than 24 hours, so I can't play it, and it won't let you,
that's a unique problem.
it ruins my,
I don't have service. So I think you don't have Snapchat.
I don't have what?
Snapchat.
No,
Dude.
I'm afraid not.
I'm on my third guess and I don't know what to guess. I just don't get a second word.
I don't know if it's maybe, yeah.
Oh, I'm assuming no other ones.
But some people.
Yeah, I was like that. I thought it was pretty.
Oh, I said my God. No, I didn't. Bro, okay. What guess you are? I'm on my fourth. I'm on my fourth as well. Okay. Dude, what? Ooh, this is it.
Okay, guys, so I think we got everybody back. I just want to go over that very last problem on this group work, because a lot of folks were still kind of working on it when I cut you off, and it's a nice one to understand how to do it, because it practices a theme that I've talked a lot about and which I've definitely put on my exams in the past, which is how do you show that the inverse of one matrix is another matrix? Answer is, as you know, that you take those two matrices, right, and you multiply them together. And when you do that, you're supposed to get what? The identity matrix, exactly. So this statement is actually a true statement. And I would like to just show you the work that would go behind showing that. If we're assuming that the inverse of a squared is b, then, so let me kind of write my solution off to the side here. That tells me that if I take a squared and I multiply it by b, I get the identity matrix. The question is, how do we then convince ourselves that the inverse of a to the 10th would be b to the 5th? Well, the answer is we would need to show that if we take a to the 10th and multiply it by b to the 5th, that we also get I. Right? Now, what I saw some groups doing, which is not a bad, it's not wrong to do it, but what I saw a lot of people doing was just taking the first equation and raising it to the 5th power on both sides. And that's not wrong, so we can certainly do this, I'm gonna write it down for a moment to just show you. Obviously, if you take 5 powers of the identity matrix, that's like 1 times 1 times 1 times 1 times 1, it's just the identity matrix again, right? But the problem is that this expression right here, a squared b quantity to the 5th, is not the same as a to the 10th b to the 5th. And that's because this thing right here, a squared b quantity to the 5th, is really a squared b times a squared b times a squared b times a squared b times a squared b, and you're not allowed to switch the order of those matrices. This is a big thing we talked about with matrix algebra. You can't switch all of the a's to the front and all of the b's to the back, which is what this is, right? This has 10 a's followed by 5 b's in that order. So if I want to get this to be equal to the identity matrix, I can't just say that it's the same as that. So how do we correctly do this problem? Well, actually, the easiest way to do it is to just write out 10 A's followed by 5 B's. That is what it is, if you want to write it all out. And then the assumption here, guys, this thing that we were told at the beginning tells us that anytime I see 2 A's followed by 1 B, I can cancel that to I. Now, if you scan this sort of long string of A's and B's, you're going to see somewhere in that string, there's 2 A's followed by a B. It may not be right at the beginning, but in fact, it's right here. In the middle of this expression, you have 2 A's followed by a B, and that is the identity. And so you can cancel that. It's like multiplying by 1. So you cancel that, and what are you left with? Well, you're left with 8 A's and 4 B's after you cancel the 2 A's and B's right there. And you look at this thing and you say, oh, I could just do that again. I have, again, 2 A's and a B next to each other, kind of embedded in the middle of the expression. So again, I can just cancel this to the identity. And if I do that, I'll be left with 6 A's and 3 B's. And you see what I'm gonna do, right? I just keep doing that. I can do it again. There's 2 A's and 1 B. 2 A's and 1 B always cancels to I. So I cancel these down to I, and I'm left with 4 A's and 2 B's. And I do it one more time. Take 2 A's and a B, combine them together and cancel them, and then I'm left with 2 A's and a B. And that is, once and for all, going to become the identity matrix. That is a kind of an interesting solution. Notice, by the way, I'm trying to be good about putting equal signs between my steps and having a nicely well-organized thing. You know, something like this, if you need some scratch paper, I'll bring some scratch paper on Thursday as well. If you want to work things out. But yeah, you have to be a little bit neat about it to get this to work out. People following that okay? Just to remind you guys, we've done 5 group works. I pulled up our Canvas page here just to show you. If you go to the files section, all 5 of these group works, the group works and their solutions are here. So if anybody wants to look at the group work solutions for the first 5, I mean, I have them all listed here, but you only need to focus on the first 5 for our exam on Thursday. So the solutions to this group work that we just did today are in there. If you want to have more time with this or practice it on your own later, you definitely can do that. Okay. Lots of stuff here, guys. If you're ever kind of like, if you forget, well, when are his office hours again? Or, you know, what should I be focusing on again? Just go to this midterm resources folder, midterm 1 resources, and you've got all these documents here. I did update the review packet. So I've got, if you open this one up, I actually did put my office hours in there now. So you'll be able to find all that stuff. You're just kind of wondering. And I'm around a lot more than just my office hours too. You're welcome to just hang out outside my office and do whatever you need to do there. Okay, I'll let you guys get the rest of the studying done kind of on your own, whatever you need to do, and I'll be around to help. I think what I'm gonna do for the rest of today is just get a little preview of what's coming next. Now, this won't be on your exam on Thursday. I hate to say that because people just tune out the second I say stuff like that, but you will need to know this. So I don't want to downplay it by any means, but I'm gonna get just a little preview into chapter 4, if that's okay. And so this will be occupying us for a good chunk of time in the month of October, right? Is that right? October's coming not too long from now. So chapter 4, the title of this is Vector Spaces. And your 78-minute extra credit video for this next weekend is going to be to watch a video that's all about vector spaces. And specifically, you'll be watching a video focusing on, I think it's sections 2 and 3 from chapter 4. What I want to do right now is just give you a quick little overview of it. So as you guys know, you spent many, many years in your grade school learning how numbers work, learning the algebra of numbers, commutative, associative, addition, subtraction, multiplication, division. You have all these rules for numbers that you guys know pretty well, I think, right? But now in this class, we've realized that actually there's some other kinds of universes besides just numbers. We could be working in a world of matrices. And if we're working in a world of matrices, the algebra, it might be somewhat like the way numbers work, but there's at least a couple places where things kind of get a little bit difficult, such as switching the order of multiplication. You're not allowed to do that in this universe, right? So you have this whole other universe of mathematical objects that are different than the ones you learned about in K through 12, right? And in this universe, you'd like to study matrices and know how the algebra of this universe of matrices works. But we don't have to stop there. It's not just about numbers and it's not just about matrices. There's also calculus functions. And there's also polynomials. And there's other mathematical objects you've worked with. If anybody's taking any physics around here, right, you talk about vectors. That's another kind of object. Well, mathematicians have realized that it really is not very efficient to have to sort of do a crash course on each of these universes separately. We're going to spend a semester doing matrices, and then we're going to spend another semester doing calculus functions, and then we're going to spend no. We don't want to be that inefficient. What we would like, guys, is one single mathematical framework called a vector space that will take care of, it's like an umbrella for all of those universes together, that we can actually study mathematical problems in any of those universes fluently. And we can translate back and forth what something means for matrices compared to what it means for calculus functions, compared to what it means for physics vectors, and so on, right? So this is going to be the idea. A vector space is a mathematical framework. So this is a mathematical framework for studying real world problems. Right, that's kind of in a nutshell what it is. That's kind of the loose definition of it. But what I'm going to have you do now, guys, is, well, so if you look in the book, the formal definition of a vector space is the longest definition in the whole book. Me and my publishers were trying to figure out how can we get this to all fit on one page. We managed to do it, but it was a little tricky. When I was sort of new at teaching this class, I would come in here and write down the whole definition, and it would take a half hour, and it would fill up all the boards. And I realized, you know what, that was really kind of not very exciting. So what I did is I made a handout, which I just passed out to you guys. I made a handout that basically has the definition on it, but with some gaps to fill in. And so we're going to fill those gaps in together right now. Okay. So what it says at the top of the handout is vector space axioms. So that's going to be basically the rules of vector space. What are the rules of this mathematical framework? So by the way, a vector space usually is denoted as V. Okay, and maybe I'll make one more point before I actually get to the handout. This vector space will it consists of objects which are called vectors. Okay, together with operations of addition. So that would be plus and scalar multiplication, which will be with a dot. So there's addition and there's scalar multiplication. Now, these objects that I'm talking about, they could be numbers, they could be matrices, they could be polynomials, they could be calculus functions, but they don't have to be any of those things. They could be types of fruit. And I could start talking about taking kiwi plus cherry and getting watermelon. There could be some, addition in quotes that allows me to take two pieces of fruit, add them together and get another piece of fruit out of that. And then I would be able to take a piece of fruit and scalar multiply it. Now, when I say scalar, I really do mean number. So I would have to take watermelon and scalar multiply it by 5 and come up with peach, something like that. So you'd have a weird system of like this framework being applied to objects that don't have any mathematical connection at all. It sounds a little bizarre. And in some ways it really is. So just the whole idea here again is that mathematicians were trying to create something so abstract and so general that we could apply this one single framework to a multitude of different types of problems. Right? That's the whole point here. Not to keep reinventing the wheel. Every time we have a new type of mathematical object that we're interested in, we don't want to have to start from scratch figuring it out. We want to know that we have at least at a bare minimum something that we're going to call a vector space that has a bunch of axioms and rules. There's 10 rules that are all going to be true. Okay, so let's look at this handout together. It says at the top, V is a non-empty set whose elements are the vectors. Okay, so that's what we're talking about. And the operations are addition and scalar multiplication. Fair enough, okay? But then there's some rules that have to be satisfied. And there's 10 of them here, okay? So on your handout, there's some blanks and we're gonna fill them in. So the spaces there. What these 10 rules are, I'm gonna tell you right now, guys, the first 2 rules are the most important ones. That's why I put them first. So, so what are these 10 rules that you're going to fill in on your little handout there? The first one is called A1, but there is another way that I'm going to write that, and you might want to put this on your notes as well. I'm going to be referring to A1 as closure under addition, and I like to denote it this way, CL with a plus. And what this one says, I'm just going to write it out. You don't need to write this all the way out because it's already typed out for you, but I'm going to write it here. So for all U and V, now I'm drawing them like you would think a physics professor would draw vectors with arrows on top of them, right? That's a good habit to get into so that you can keep the vectors straight from the scalars, for example. For all U and V in the vector space. Now, here's where you need to fill in on the handout. U plus V is an element of that vector space. So remember this belongs to symbol? We used it earlier in the semester when we were writing the solution sets to systems of equations. Guys, what this just means is that if you quote unquote add two vectors together, the result has to be another vector in that same vector space, in that same universe. So if I take apple plus cherry and say that it is equal to green, that doesn't make any sense. I'm taking two fruits and I'm adding them together. I better get another fruit again. I have to get something that's in the same universe. Does that make some sense? So that's closure under addition. This is super hugely important for linear algebra. If two objects are in the set, then after I add them together, the result should still be in the set. You're going to have 78 minutes of me really harping on this one, because if this fails, then you don't have a vector space and it's game over at that point. You don't, the rest of this sheet becomes irrelevant and you can't do anything. We really need the closure under addition. Now, going right along with that is the A2 axiom, which I also like to denote as closure under scalar multiplication. And so I like to write that with a CL with a dot on it. Okay, because we have two operations, right? We have addition and we have scalar multiplication. And this just says, again, it's partially typed out already for you on the handout. You just have to fill in the rest of it. For all V in V and scalars K in R, here's what you need to write. K dot V is still in V again. It's still in V again. Okay. Just to give you a quick example, just so you kind of have an idea. Let's say that I tried to tell you that the positive numbers are a vector space. Numbers that are greater than 0. Well, you know what, guys? The numbers that are greater than 0 fail this axiom. Because if I take a number that's greater than 0, that could be my vector, and I multiply it by a negative scalar, I no longer have a number that's greater than 0 anymore. So it fails to be closed under that operation at that point. So if either one of these two axioms fails, we do not have a vector space, and it's not going to matter what happens with all these other axioms. Most of the rest of the axioms on this list, guys, most of the rest of these rules in this handout are much more natural and don't require as much attention. These first two require a lot of attention. So when you're watching my little video for extra credit this weekend, you'll see me talking a lot about these two rules, okay? I'm not going to do a lot of examples right now, just because I know those examples are in, there's a good number of them in that video that you're going to watch. But let's go on. There's 8 other axioms here, guys. There's A3. And now on this one, it just says commutativity of addition. Okay, if you look at A3 on your little handout there, and what it says is for all U and V, now I'm going to write the equation that you need to write next to A3. It's just U plus V equals V plus U. That's commutativity of addition. So if I add two vectors, doesn't matter what order I do them in. I know that's true for numbers. I know that's true for matrices. I know it's true for physics vectors, right? These are all good examples of vector spaces. This one is almost always true, unless you come up with a weird universe where strawberry plus banana is equal to orange, but banana plus strawberry is equal to kiwi. That wouldn't work, because now strawberry plus banana didn't give me the same thing as banana plus strawberry. It would have to be some concocted vector space with weird operations. But if we're working in familiar types of mathematical structures, this is kind of a freebie almost. It's almost always going to be true. A4 is the same way. It's the associativity of addition. This one just says that if I take 3 vectors, U, V, and W, and I want to add them all together, that the parentheses don't matter. So I can get the same answer no matter what order I do that in.
I suppose I could do something really weird. And I'm not trying to confuse you. It's just this kind of weird stuff. I could say that my addition operation is going to be what I regularly think of as subtraction. So if I did that, I think we would all agree that subtraction has problems. Right, and if you tried to subtract three numbers in two different orders, you get two different things. So subtraction does not form a valid operation to play the role of addition in a vector space, if that makes any sense. Anyway, it's kind of weird. I won't be playing with weird examples with you guys very much. If you want the weird examples, you just have to change your major to math. And next semester, take Math 307, and you'll see all of these examples in the more, I guess, abstract linear algebra class. Okay, A5 is an important one. Let's kind of spend a minute to talk about this one. This is existence of a zero vector. So existence of a zero vector, and what it says here, guys, is that in V, there is a vector. And it's written just with zero, and I like to put an arrow on top of it to emphasize. You notice I've got bold print on the handout. Anywhere where there's bold on this handout, when I'm on a whiteboard, I can't do bold very good, so I'm just using arrows to emphasize that it's a vector. There is a vector satisfying, so here's where you're going to fill in the rest of this statement. 0 plus V equals V. This is what you need to write down on that handout next to A5. And that's for all V in V. So if I happen to notice that that cherry plus grape is equal to grape, and cherry plus strawberry is equal to strawberry, and cherry plus orange is equal to orange, and cherry plus kiwi is equal to kiwi, that sounds like cherry is like playing the role of 0. When I add it to anything else, it just leaves it alone. Right? So we have to have a zero vector in any vector space. In the world of matrices, we have one. It's this guy, right? The all zero matrix. When you add that to anything, you just get that same thing back again. I like this one, by the way. It's sometimes, because we're going to have a lot of negative examples of things that don't work. And when something doesn't work, this one can often be a quick no. If you notice that your zero vector is not part of your universe, then you know you don't have a vector space. Because every vector space, according to A5, must have a zero vector. Can I give you a quick example of that? Since we've been talking about matrices a lot. Would the set of n by n invertible matrices, this is a yes or no question, would the n by n invertible matrices themselves be a vector space? Let's just say we're adding matrices in the usual way. We're scalar multiplying them in the usual way. Would the invertible matrices form a vector space based on what I've just been talking about?
No.
I don't think so. I don't think so, because the zero vector, as we know, is this matrix. And is this matrix invertible? I don't think so. It is actually going to have a determinant of 0. The zero matrix is not invertible, and so it's missing the zero vector. If you take all invertible matrices, you're missing the zero vector. So it fails this axiom, this rule. By the way, guys, if any one of these 10 rules fails, it's game over, right? It's not a vector space. You can stop. You don't have to look at anything else. Let's keep going. A6. A6 talks about additive inverses. So it says, this is also kind of a nice one to understand a little bit. For each vector v in V, I'm just writing what's on the handout here, guys. There exists a negative of that vector in V such that, and now here's where you need to write the equation in on your handout. You need to write V plus negative V is equal to 0 vector. So that goes with A6. So there has to be a vector that cancels out any other vector under addition. So if you've determined that your zero vector is cherry, and then I hand you strawberry, and I say, well, what is the additive inverse of strawberry? Well, you're looking for something you can add to strawberry to get back to cherry again. So it has to cancel it out back to whatever the zero vector is in the universe that you're playing in. Yeah. It's weird stuff, isn't it? I know I thought it was when I first learned this. A7 is an easy one, and this one, unless somebody gives you a really funky scalar multiplication operation, this is not ever going to be an issue. Which I won't be giving you weird operations usually. But number A7 just says for V in V, we have 1 times V is equal to V. A lot of people will look at that and say, well, isn't that duh? Isn't that like obvious? It should be true. Maybe not so obvious if I don't know exactly how I'm doing the scalar multiplication. If I'm in some universe that I've never seen before, maybe scalar multiplication behaves in a non-standard way, something not intuitive, and maybe this is actually something that takes a minute's thought to see if that's actually going to be true or not. So, but it is required for a vector space. Okay, the last three, let's just jot these down pretty quickly. For all V and V and scalars R and S, we have the following. I'm going to write it down here, guys. RS scalar multiplied onto V should be equal to R scalar multiplied onto S scalar multiplied onto V. So there's some kind of an associative property with the scalar multiplication there. And then for the last two, I'm going to bring in the addition again. A9 just says for all U and V in V and scalars R, we have, let's write it down here, R scalar multiplied onto U plus V is R scalar multiplied onto U plus R scalar multiplied onto V. So it's what you would expect, I think. It's a normal looking property that has to be true. Okay, and finally, A10 is pretty much the same thing except with the addition of being done with the scalars. So A10 would look like this. If we have two scalars R and S that we add together and we scalar multiply that onto my vector V, that should be R scalar multiplied onto V plus S scalar multiplied onto V. So nothing very strange about these last axioms. The most important ones, the ones that we're going to be having in our face most of the time are going to be A1 and A2 and sometimes A5 or A6. The others are all pretty much just algebraic properties that you don't have to worry about too much. I wanted to point out, if you go to our Canvas page, there is a folder called Special Handouts. I think I've shown you this before. There's a bunch of documents in here. I wanted to point out the very last document in this folder is actually this handout. And on this document, I've actually got it all filled in already. I just wanted to make you guys write something down today to keep you awake, taking some notes. But on this handout, it's already been filled in. So if you lose track of this piece of paper and you want to find this again, it's just called vector space axioms. Axioms are just rules that have to be satisfied for a definition. It's really, really what we're talking about. Any questions about this kind of abstract idea here? I don't want to do a long list of examples because those are mostly in the video, but I am going to give you one example right now so that I can come back to something I mentioned about determinants. So I'm just going to do one example here, which is, here's a good example of a vector space. We'll just do one right now, and it's basically Rn. It's basically Rn. This is a very familiar vector space. When you worked in Math 250A, you would have been working with R2 and R3 a lot, right? Your XY plane is like R2. Your XYZ space, that's R3. It's basically something that can be written as a set of n tuples. So there would be like n slots here, say x1 and then x2 and then dot, dot, dot up to xn, such that, so I'm using my little notation that we learned in chapter 2, such that x of I is an element of the real numbers. So this is actually an example of a vector space. Actually, to verify that is a royal pain, because to verify that anything is a vector space, I actually am required to check this entire list of 10 things. And you can see why that would take a long time. In the book, I did write it out for a few examples when I typed up the book. I was screaming at the publishers about it. It's like, this is taking up so much space. But it does take a while to write down all of these rules. I won't be normally asking you to do that. I will mostly be asking you to just focus on the first two, for reasons that I'll explain in that video that you're gonna watch. The first two axioms, generally, we do need to really hone in on those and check those carefully. Beyond that, we don't really need to do that much. So these are done, these n tuples are computed using the ordinary addition. So I'm just gonna say using regular slot by slot addition and scalar multiplication. So you would have that, and this is a valid vector space. This is a vector space. So Rn is a nice example. Actually, it's not just one example, it's infinitely many examples. There's R1, R2, R3, R4, R5, R6. These are all different universes that we can work with. Okay, and I think everybody, if I gave you a bunch of physics, these are basically like physics vectors with slots. If I gave you a bunch of vectors, you could add them, you could scalar multiply them, you could play around with the 10 rules here. It wouldn't be terribly interesting. Nothing goes wrong. Nothing is very exciting. It's just regular math arithmetic for the most part. So that's one example. There are many others. I've already been hinting at them. Calculus functions, matrices, polynomials. There's lots of examples that we're going to be working with, but we're going to have this one framework of a vector space that sort of is the umbrella under which all of these other universes can be kind of understood. Okay, I want to go back to something that's not on the handout now and tie back in one thing I said about determinants. Do you remember, so this is called this a follow-up to this little example here. You remember that I mentioned there was a fourth application of determinants, and that was that they have a geometric interpretation. So let's just recall that here. Recall that if A is 2 by 2 or 3 by 3, so we're going to keep n equal to 2 or 3 for this, then the determinant of A gives a geometric interpretation. And I want to explain it, and it'll be kind of in terms of the vector space Rn. That's why I'm talking about it right now, of all times. But let me find my little note here. It's actually going to be sort of two parts here. So I'll write down part A and then I'll write down part B. Part A is if A is 2 by 2. So if my matrix capital A is 2 by 2. In this case, guys, the determinant of A, and by the way, even though this is about determinants, don't worry, I'm not going to put any of this on the test. Thursday. We haven't had any homework on this, we're just talking about it right now. This is really gonna be more relevant for chapter 4 anyway. So I just wanna get it out there ahead of time. But this is a number that somehow has a geometric interpretation. And what is it? Well, it turns out that it measures the area of the parallelogram. Spell that word? I don't know, parallelogram, I think is, hope that's right. Determined by the rows, and I'm gonna put in parentheses, or columns. The rows or columns of A. The area of the parallelogram determined by the rows or columns of A. I need to make a slight little edit to this. When we talk about area, we are never going to allow that to be negative. So we're actually going to need to take absolute value bars around that determinant to make sure we have a positive number here. But just so you have an example in front of you, let me just show you what I mean. Let's just take A to be the matrix, I don't know, 5 and 1, and then 1 and 4, something like that. And if we look at the rows of this matrix, right? By the way, each row is like a vector in R2, right? 2 slots here, 2 slots here. So these are 2 vectors in R2. And I could actually draw a picture of R2. This is a vector space, as we just discussed. In R2, I can draw the vector. Let me just make some tick marks here. I can draw the vector 5, 1. Just visualize that for a second. And then that's like the first row. And the second row would be 1, 4. So I'm going to draw the vector 1 and 4. Okay, so this is, let's just call this first vector V1. That's the first row, and the second vector is V2. And so we can draw those 2 vectors visually in this R2 picture. And then you see we can extend it, guys, and make it into a parallelogram. So when I say that it's the parallelogram determined by the rows or columns of the matrix, that's what I'm talking about, is basically you can draw the dotted sides just parallel to the original vectors. And that gives you something right here, guys, that has an area. And this area is supposed to be the absolute value of the determinant of this matrix. What is the determinant of this matrix, by the way? 19, right? 5 times 4 minus 1 times 1, that's our little 2 by 2 determinant trick. 20 minus 1 is 19, and so that area is 19, right? So guys, this determinant, actually now the number itself actually means something. It's not just whether it's 0 or not, but we actually care about the number itself, like the fact that we got 19 and not 18 or not 17. That number is the area of that blue shaded region, if that makes sense. Okay, and there's something very similar to that for the 3 by 3 case. So let me give you that and then we'll kind of wrap this up. If A is 3 by 3, in this case, if we take the absolute value of the determinant of A in this case, so we're here for a second. In this case, the absolute value of the determinant of A measures not the area, but the volume, exactly, the volume of the, not the parallelogram, but the, what's the 3-dimensional box called? If it was square sides and everything was 90-degree angles, it would be a cube, but we have to be a little more general than that. It's called a parallelepiped. Have you seen that word before?
Yes.
Parallelepiped. I don't even know if I have anything remotely like the right spelling of that. I hope I have it right. The parallelepiped determined by the rows or columns of A. And I want to give you one quick example of that too. It's really a useful one for where we're headed in chapter 4. Let's say that we take A to be the matrix 1, 2, 3, and then the second row 4, 5, 6, and then the third row 7, 8, 9. Now, I'm not going to try to draw this parallelepiped. I would have to draw XYZ coordinate system and figure out how to make these vectors look nice. And I don't think I'm a good enough artist for that. But I'm going to give you a little hint that if you calculate the determinant of it, does everybody know how to find the determinant of this?
Yes.
I hope so. It's the arrow method, or you could use cofactor expansion, even on a 3x3. But I'm just going to let you check, because I don't want to spend the time. I've only got like a minute left here. I don't want to spend the time on it, but I'm going to let you check that that determinant is actually 0. So in other words, this matrix is not invertible. But let's think about it from a geometry point of view. What that tells you guys is that the volume, so if I was to write down these 3 vectors and plot them in the XYZ plane, and I create this parallelepiped, how much volume does it have? If you believe me. None. What does that mean about the 3 vectors? If 3 vectors are not actually forming a 3-dimensional shape, then what are they forming? Or what would have to be true about those vectors? Yeah, they're actually all kind of tied up in the same plane. Like they're all kind of, pointing in, it may not be exactly the XY plane or the XZ plane or the YZ plane, but these 3 vectors are all in the same plane, right? So these vectors are in the same plane. And in fact, I'm going to really convince you. I hope that I'm going to really convince you. The last thing for today, guys, that middle vector, I can write it in terms of the other 2. It's half of the first one, 1, 2, 3, plus half of the third one. And if you check out the math on that, it really is true. In other words, the second vector is half of the first vector plus the third vector. This really means that there's what we call a linear dependency among these 3 rows of this matrix. The 3 rows are linearly dependent. I can write one of them in terms of the other 2. This is a concept we're going to come back to next week after we get done with this midterm and all that good stuff. But I wanted to at least expose you to it briefly today, that we can actually use determinants to create equations between vectors. Pretty neat. I wish I could go on. I could go on for hours about this. I love this stuff, but I really should stop and let you get on with your day. I do have office hours right now downstairs for a little while, and also tonight after 5:30, and tomorrow, and the next day, and the next day. Pretty much every day. Feel free to stop by and study well. Let me know what I can help you with.
Yeah, do it all.
One second.